Cosmic ray-boosted dark matter is revisited at IceCube, focusing on lower energy data than previously considered. The authors explore the upscattering of dark matter by cosmic rays, which can accelerate ambient dark matter, making it detectable at high-threshold, large-volume experiments like IceCube. This process involves both elastic and deep-inelastic scattering with electrons and nuclei. Despite its overwhelming evidence and majority composition of the universe, dark matter remains undetected non-gravitationally. Underground direct detection experiments have been searching for weakly interacting massive particles, WIMPs, in the 1 GeV to 100 TeV mass range. However, dark matter could be too light to trigger recoils in typical large detectors. To circumvent this, the authors propose searching for electronic recoils produced by very light dark matter, accelerated to high velocity, increasing the energy it can deposit in a detector. The authors revisit cosmic ray-boosted dark matter signals at IceCube, considering lower energy data than before. They consider two benchmark models, Fermion dark matter with vector and scalar mediators. Comparing their model projections with the most current constraints, they show that IceCube can detect cosmic ray-boosted dark matter, especially with masses below 100 keV when scattering with electrons and MeV in the nucleon scattering case. The authors discuss upscattering by cosmic rays, propagation through the ice to the IceCube detector volume, comparison of the dark matter event rate to IceCube data, and the resulting limits. They also explore deep-inelastic scattering and dark matter nucleon scattering using the same framework. By incorporating lower energy data, the authors improve sensitivity and provide limits using two benchmark models, building on previous studies that have yet to be explored at detectors like IceCube. The flux of upscattered dark matter due to collisions with cosmic ray species is calculated using equation 1, which incorporates the local dark matter density, dark matter mass, and outgoing dark matter kinetic energy. The cosmic ray spectrum is modeled based on the local spectrum of cosmic ray electrons measured by Veritas, extending into the TeV range. The spatial distribution of dark matter and cosmic rays is absorbed into an effective distance parameter def, resulting in the simplified formula 2, with def set to 10 kpc, consistent with recent works. Two interaction models are considered: fermionic dark matter scattering via a vector mediator, with a differential cross-section given by equation 3, and fermionic dark matter scattering via a scalar mediator, with a differential cross-section given by equation 4. The recoil kinetic energy of the dark matter is given by equation 5. The flux of upscattered dark matter reaching Earth is computed using these cross-sections, assuming complete blocking of dark matter propagating toward IceCube from below the horizon and considering only downgoing events. Half of the total dark matter flux is assumed to arrive from above the horizon, a conservative estimate. Propagation of dark matter through at least 1.45 kilometers of ice to the IceCube detector volume is modeled using a modified version of the new FATE software, assuming straight trajectories for the dark matter particles. The effect of the active veto layer in the detector volume is taken into account, and only dark matter particles that scatter exactly once in the detector volume are considered. The authors utilize data from IceCube, a neutrino detector, to search for signals of CR-boosted dark matter (DM). They analyze 641 days of contained neutrino events reported in reference 54, which provides measurements of astrophysical and atmospheric neutrino fluxes down to energies of approximately 1 TeV. This low-energy dataset is chosen to maximize the detectable flux of DM particles, given the steepness of the galactic CR spectra. The event rate is computed using equation 6, which depends on the energy transferred from the DM to a target electron, exposure time, Avogadro's number, and the energy-dependent effective mass. The effective mass is calculated from the effective area reported in reference 54. The authors compare the spectrum of DM-induced events with the observed events reported in reference 54, focusing on southern sky events and assuming an isotropic incoming DM flux. A binned likelihood analysis is performed, including background components such as atmospheric neutrino, astrophysical neutrino, and penetrating muon fluxes. The likelihood is defined in equation 7, and the test statistic is given by equation 8. The authors rule out a value of the mediator mass if the test statistic is greater than 2.71. Figure 1 shows the energy spectrum of southern sky events observed by IceCube, compared to an example spectrum of DM events for a vector mediator. The authors then proceed to set limits on the non-relativistic DM electron cross-section by scanning over the mediator mass for each value of the DM mass, following a similar approach to reference 9. This research paper delves into the experimental constraints on dark matter, DM, interactions with electrons and nucleons, focusing on scalar and vector mediators. The authors present their findings in the context of IceCube, Super K, and Panda X4T experiments. They provide limits on the non-relativistic DM electron cross-section for both scalar and vector mediators, showing that these constraints are competitive with or stronger than those from other experiments. The paper highlights how the scattering rates differ between scalar and vector mediators due to their differential cross-sections. In the scalar case, scattering is heavily weighted towards large momentum transfer, leading to a point where reducing the mediator mass does not increase the scattering rate and thus attenuation. Conversely, in the vector case, making the mediator mass small leads to a large scattering rate in the ice above the detector, resulting in a ceiling for the cross-section limits. The authors also delve into the case of DM proton scattering, which is complicated by the high energies involved, requiring consideration of both elastic and deep-inelastic scattering. This section sets the stage for further analysis of DM nucleon interactions and their implications for direct detection experiments. Deep-inelastic scattering, following Ref. 15, is discussed in the context of dark matter, DM, scattering with protons. Assuming DM couples equally to all quarks, the scattering cross-section is derived. In the low momentum transfer regime, the elastic scattering cross-section is given by equation 13, where beta is the incoming DM velocity, E chi is the incoming DM energy, and Q squared is the momentum transfer. The proton form factor, Gp, Q squared, is modeled using equation 14, with lambda p equals 770 MeV. In the high momentum transfer regime, the deep inelastic scattering dis cross-section is given by equation 16, equivalent to the vector mediator case. This cross-section is expressed in terms of the Parton distribution function, PDF, of quarks within the nucleon, f squared, x, q squared, where x is the Bjorken x variable. The CT10NLO proton PDFs, obtained using LHA-PDF, are employed. For the scalar case, the dis cross-section is given by equation 18, in the ultra-relativistic limit. Resonance excitations, important in the intermediate regime, are neglected in this analysis, as their modeling requires in-depth modeling of hadronic states within the nucleus. This assumption is justified, as upscattering of light DM should be dominated by quasi-elastic scattering, and energy deposition in the IceCube volume will be dominated by dis. The dark matter flux at IceCube is computed by considering upscattering by proton cosmic rays, CRs, only. The CR proton spectrum is obtained by interpolating the Dampy measurement of the proton flux. The upscattered flux is computed using equation 2, replacing the elastic cross-section with the sum of elastic and inelastic cross-sections. Due to the steep slope of the CR spectrum, the limits will be set by the low-energy end of the IceCube data, around 1 TeV. Inelastic processes become important for momentum transfers above tilde 100 MeV, which is not significant for most of the parameter space considered. The authors present the results of their analysis on the limits of dark matter proton scattering cross-sections for scalar and vector mediators. For scalar mediators, Figure 4 displays the limits across 3 choices of coupling, with mediator masses ranging from 40 MeV to 2.7 JeV. The gray exclusion region is based on cosmic ray-boosted dark matter interacting in Xenon1T, where only deep inelastic scattering is considered in the attenuation calculation as it is the dominant energy loss mechanism. For vector mediators, Figure 5 shows the limits across 3 choices of coupling, with mediator masses ranging from 11 MeV to 3.9 JeV. The gray exclusion region is based on cosmic ray-boosted dark matter interacting in Xenon1T, while the dashed black line represents a limit on new vector mediators from a previous study. The authors compare their results with existing exclusion regions from previous studies, including Ref. 9 and Ref. 10. Notably, their limits are comparable to the constraint on a baryon number-coupled vector mediator from Ref. 74, which arises from anomaly cancellation considerations. The significance of their results lies in pushing the limits of direct detection constraints down to the Kev scale for both dm electron and dm nuclei on scattering, overlapping with the Fartern goals laid out in a recent review. To achieve these results, the authors employ a methodology that involves fixing the value of the product of the couplings and varying the mediator mass to vary the cross-section. They utilize a statistical approach to set limits on dm proton scattering, requiring that the dm event rate never be significantly larger than the total observed event rate. This research paper delves into the realm of dark matter, a hypothetical form of matter that is thought to make up approximately 27% of the universe's mass energy density, yet remains undetected by direct observation. The authors explore the possibility of detecting dark matter through its interaction with cosmic rays, which are high-energy particles originating from outside Earth's atmosphere. They focus on two benchmark models of Fermion dark matter, utilizing vector and scalar mediators as interaction mechanisms. The paper begins by discussing the current understanding of dark matter, citing various studies that have attempted to detect it via different methods. It then outlines the approach taken in this study, using cosmic rays as a potential source for upscattering dark matter particles, which could then be detected by the IceCube neutrino observatory. This novel method is based on the assumption that dark matter particles can interact with cosmic rays, causing them to scatter and produce high-energy neutrinos that can be detected by IceCube. The authors detailed their calculations of the dm flux from cosmic ray upscattering and derive limits on the non-relativistic scattering cross-section. They find that for electron scattering, their limits are comparable to or stronger than existing cosmic ray-boosted dark matter limits, depending on the choice of coupling. For proton scattering, the limits are substantially stronger than existing cosmic ray-boosted dark matter limits over a wide range of masses. Additionally, they discuss how the limits could be improved with more detailed modeling of the galaxy's geometry and future upgrades to the IceCube detector. The paper also compares their findings with other recent studies on dark matter detection, highlighting the novelty of their approach and the potential for future improvements in sensitivity. They conclude by emphasizing the importance of continued research into this area, as it may provide crucial insights into the nature of dark matter. In terms of methodology, the paper employs a combination of theoretical calculations and comparisons with experimental data from various particle physics and astrophysics experiments. Key terms and concepts include dark matter, cosmic rays, neutrino detection, and scattering cross-sections. The equations and algorithms presented are primarily used to calculate the dm flux and derive limits on the scattering cross-section, utilizing various assumptions about the dark matter models and interaction mechanisms. Overall, this research presents a new perspective on detecting dark matter through its interaction with cosmic rays, offering promising avenues for further exploration and refinement. It seems that there is no content provided to refine. Please provide the transcript you'd like me to refine, and I'll be happy to assist you in creating a concise, technically accurate summary of the research paper for voiceover narration. In conclusion, the research paper emphasizes the importance of continued investigations in high-energy astrophysics, particularly focusing on the detection and analysis of cosmic rays and neutrinos. Building upon the foundational work of Faisley and Yoon et al., this study leverages high-energy neutrino telescopes such as IceCube to gain insights into astrophysical processes and the origins of high-energy radiation in the universe. Precise measurements and advanced data analysis techniques are crucial for identifying potential sources of high-energy particles. Multimessenger astronomy, which combines observations from different types of detectors, is also highlighted as a key approach to comprehensively understand cosmic phenomena. Ishihara's work on IceCube underscores the ongoing efforts to enhance our understanding of these phenomena through cutting-edge experimental techniques and data analysis methods. This includes the development of new algorithms and statistical tools to identify patterns and correlations within large datasets. The paper ultimately underscores the necessity for precise measurements, advanced data analysis techniques, and multimessenger astronomy to uncover the mysteries of the universe's most energetic events.